Hello! Today we will learn how to use pw.x for finding the equilibrium relaxed geometry of a molecule. Then we will learn how to use xcrysden in order to visualize a molecule, the structure of a molecule, and to obtain information about bond lengths and bond angles. We start with the input file we used in the tutorial number 1. We copy it in a new file we call methane underscore relax.in, and we edit it. First, we change the calculation from SCF to relax. Then note that we will use an energy cutoff for defining the plane waves as large as 60 Rydberg, as we shown that it is appropriate. Now, to speed up the calculation, we can here use the diagonalization strategy, Davidson, so the Davidson algorithm, and we put instead of CG, David. We must now add another name list, which is called ions. It is sufficient to left it empty. Now we can save the file and we are ready. For visualizing our structures, so in this case the structure of the methane molecule, we will use the software called xcrysden. You can get that code either from the website www.xcrysden.org or as a package in most of the Linux distributions. We can invoke now xcrysden. Now we go to File, open pw's SCF, open pw's SCF input file. Then we select our input file methane underscore relax.in. We close it and we do not reduce dimensionality. This is our input structure. We can rotate it, and these lines, the box, are the periodic boundary condition. If we don't want to display it, we click crystal cells. We are now ready to perform our calculation, whose goal is to find the geometrical configuration of the atoms for which the atomic forces are 0. So our input file is methane underscore relax.in, and we put the output from standard output to methane underscore relax.out. We can see it as it goes. It is. And we see that the code performs several DFT calculations, self-consistent DFT calculation, updating one after the other's calculation the position of the atoms. Then it reaches convergence. Let's have a look at the output file. It's important that at the end of it, WSCF tell us that the final coordinates are these ones, and is important to notice that are slightly different of the original ones. At the beginning, remember, we had 11.2 and we have a slight optimization. Indeed, we started from a structure close to the equilibrium 1. In most of the cases, this is not true. Remember. Note that the final coordinates, the equilibrium coordinates, depend on the choice we have made for the exchange a correlation functional. In our case, remember pw.x, normally that choice of the functional is done by the selection of the pseudopotentials used. Let's now visualize the final structure we got. We go to File, open PW-SCF, open PW-SCF output file, and we select our file methane_relax.out. Open, close, do not reduce dimensionality. Then we select display optimize coordinates, which are the final equilibrium coordinates found by pw.x. Okay. And now we can measure the distance carbon hydrogens. For this, we select distance, then we select the first atom and the second one. We press done and we get the distance here in angstrom, but we can also have in Bohr and in units of the crystal. We can also measure an angle. Let's, for example, measure the hydrogen-carbon-hydrogen angle. Let's press angle. We select the first atom, hydrogen, the second one, and the third one. Done, as expected, 109.471 degrees. You can find the input file we used on this website, www.gwl-code.org.